Great. So the work I'm showing today, as is so often the case, is built on the efforts and contributions of many people at NSLSII, at our peer facilities in the DOE, and at our international collaborators in the Bluesky project. I've named on this slide those who had a particular effort to lift these demos up today. So we have live demos for you. Yesterday, we recorded live demos with Beam at 2 Beamlines at NSLSII. We really thought about doing this actually live on this call, but a 25-minute talk does not give a lot of room for the gremlins that tend to plague and slow down live demos. So you're getting a tight presentation today. We think it probably would have worked live. I guess we'll never know. We're going to show two different approaches here, a desktop-based application and a web browser-based application. And without getting into details, I just want to point out that both of these are remote friendly, right? The desktop app could be running on a user's laptop at home and connected securely to the Beamline network. Web apps are very naturally remote friendly, or either of these could be running at the Beamline physically, at the Beamline, or over a remote desktop client. So it's really just two different ways of working, desktop and web, both remote friendly. Two Beamlines, alike in dignity. BMM and PDF have agreed to be the victims and presenters of this demonstration. So we'll turn most of the time of this talk over to them. I want to focus your attention in today's demos on the toolkit, not on the specific applications. I'm proud of the applications. They're good. They did scientific measurements. They're a promising and exciting start, but they're not the emphasis. They're still what we consider very early work. And we're mostly interested in how quickly we can put together applications like this, because we think many different Beamlines have vastly different needs in terms of what they want their users to see and the workflows they want to make easy, but they're built on a common core. And just as we've always approached with Bluesky, there's this some assembly required ethos, where out of the box, it does some things, it will work for you, but what you probably want to show to your users is going to require a little bit of assembly and a little bit of customization. In exchange for that, it's very easy to build a complex and interesting and original applications. So that means that you just need an investment from either a software-oriented Beamline staff, a postdoc that they hire, or the scientific software support staff at the facility. We're navigating a sort of social question here, right? Software reflects the organizations that it's developed in. And specifically, we're navigating this tension between wanting to share and to automate the boring parts, as they say, to share the bug fixes and the documentation, to build up this broad knowledge base across the facility staff and their users, where we can avoid variation that we don't need, but we need to leave space for people to specialize and to differentiate themselves. Of course, Beamlines are incentivized to do something no one else can do, to provide something for users that no one else can provide. As an example of that, you'll see today this new app at BMM called Ariadne. That branding, that name is BMM's. The core functionality is relying on this shared code going all the way down to I guess, Linux and Epix and Python, and then going up through Bluesky and these core libraries we've developed over the years. But BMM may add Beamline-specific functionality to Ariadne, both in the interface and in the actual scientific functionality. And we can negotiate over time what should be core and what should be BMM's particular responsibility. And this is how we can share and differentiate at the same time. Now, as many people on this call will know, our first target with Bluesky back in like 2015, I guess, was users coming from spec, this terminal-based so-called read, eval, print loop, REPL-based workflow, where for one thing, you've got a text interface, but more deeply than that, the way that you're working tends to be try a thing, see how it goes, try another thing, and you're generally glued to the keyboard. Maybe you walk away overnight after setting up a really long scan, and then you'll see in the morning how it goes. But a fundamentally different way of working is with a queue. Sort of imagine a spreadsheet of tasks to be done, but one that you can edit while data acquisition is happening, moving rows around, changing configurations, adding things. This editable queue is a new way of interacting with Bluesky, with scan orchestration. At least in Bluesky's world, this is new. It works on all the same Bluesky plans, all the same Beamline configuration carries straight over, so no new device configuration to do. And it can be easily populated with an Excel spreadsheet. Users show up, upload an Excel spreadsheet, and now they have a queue of scans to run. And you'll see us demo that, I think, twice today. But unlike an Excel spreadsheet, you can safely mutate that queue. You can rearrange the order that things will be done, add and remove during acquisition. This way of working it tends to be the kind of thing that people want in a graphical interface, right? When they think about a scanning GUI, a queue seems to naturally fall out of that. So we built a desktop-based and a web-based interface to that. We're working on a Jupyter-based one. But of course, command line control still works, and you'll see that as well. Here's a glance at the graphical interface for the web. On the left, you see the queue. On the right, you see the history of scans that have been done. And then in the middle, a plot from a scan in progress. And here's a peek at the graphical interface on the desktop, where again, you see a queue in these views. And in the bottom right, you're looking at a view of Data Broker, where you can do search queries and then plot data in the same way that it would be plotted from a live scan and compare old data to data coming out live. We'll see all of this demonstrated in a moment. A key detail that I want to land before we get to the demos is that there's a separation between these applications and the software that's running the queue and ultimately talking to the hardware through epics. This means that if the app is closed or if it crashes in the middle of the experiment, nothing is lost. Acquisition continues anyway, and you just restart the app, reconnect, and you'll see where the queue was and what has happened since you last checked in. This separation also gives us space to provide a kind of access control. And this can be interpreted in both a positive and sort of a negative protective sense, right? In the positive sense, we're putting guide rails on what the user can do to give them fewer options to choose from. We're saying, here's the list of plans that you can run, the list of scan types perhaps, and here's the hardware that you're allowed to run them on, and it's not too many choices. It also means that we can enforce that only certain hardware and certain procedures are available to certain users. And you should notice that this is both, it's sort of in the middle of the security that's available today, right? Security from epics gives you PV by PV access controls, which is a little finer grained than we tend to think at the science level, or just says you're either in the beamline network or you're not. And that's a little coarser grained than we think. So it's a different way of implementing security, a different level of security that may be convenient from the point of view of science. Because this app can run on a different machine from the queue, it's very easy to make this remote. And you can also connect multiple apps to the same queue. So you can imagine multiple different apps of different types observing or controlling the queue at the same time, which gives us a path toward interleaving multiple users' requests, or even having a user and an automated, say, AI-enabled agent adding or removing things to the queue or reprioritizing. So there's lots of interesting potential in this idea of an experiment queue connected to a user-facing application. So with that, it is demo time. I'm going to have to reshuffle a little bit. I will play a video while my colleague Bruce Ravel narrates. Bruce,
yes, I am going to be narrating these videos that we recorded yesterday at BMM. So everything you're about to see is real data with real X-rays on real samples recorded yesterday. Going to start with the web interface. Clicking on the Actions button, you see that there's a list of all of the commands that we regularly use to run the beamline, the things that we want our users to be able to do. Each one gives you an interface, a form that you can fill in to make that action happen the way that you need it to happen. But instead of showing you building a queue piece by piece, what we normally do at the beamline is have our users fill in these spreadsheets that describe a whole experiment. And what I'm going to show you here in a second when it moves forward is how we import one of these spreadsheets to build a list of pre-prepared plans and create a queue out of it. So I just imported that spreadsheet, and it put in a sequence of 5 plans. The slot command is the one that puts the correct sample in the beam path, and the xaths command is the one that, well, measures the xaths. So we start the queue, and one by one, we'll go through the list of things in the queue. The first thing it did was move the correct sample into the beam path. And here in a sec, it's going to start showing you data that is coming in what was at the moment real time. Now, there is a point I really want to make here. Well, there's sort of 2 points that I really want to make here. First off, we're able to understand what's in the queue and what's been in the queue. The things that I'm showing you right now are the details of each of the plans. Not presented in the most beautiful way right now, but you can see how things are going to be done and how things were done in the history. Because it's a queue, we can edit things that are coming up. That was the thing I just showed you. There was the opportunity to edit the details of the xas command. And what I'm showing you right now is that you can rearrange things in the queue, which doesn't really make sense in this context. They need to happen in that order, but you have the ability to rearrange things that are upcoming in the queue. Now, the point I really want to make in this first video is that this is built off of existing things. That is, at the Beamline, we've been using the BSUI command line interface to the Beamline for 3 years now. We have a set of plans that do our work well. They're well tested. They do the things we need them to do. This isn't new stuff that I'm showing you right here. This is the web application talking to the queue server, talking to the run engine, and having the standard plans at the Beamline just happen in this graphical web-based context. The thing you just saw me do was switch between 2 different views of the data that's streaming in real time. That to me is a really profound point. We're not replacing what we already have at our Beamlines. We're building upon all of the effort that we've already put into the Beamlines. Now, what you just saw happen is that we moved to the second sample, and now we are moving on and measuring the second sample. The results of the previous xs measurements are available for you to examine in the history column. So Dan, I think this is one of those moments where I'd like you to click forward by 30-second increments, basically speed up time through this measurement. Exactly. Yeah. So go all the way to the end. Just if you could just step forward, step forward, step forward. Need to keep something on time. So you see this a couple of minutes later, and this is coming to its conclusion. The first sample we measured was a nickel foil. You're seeing here the end bit of the nickel oxide sample being measured. And that's the web interface to the queue server. The next point I'm going to make is that the queue server is independent of the interface. And so what I'm about to show you now is the Qt interface. We're going to go through the same sequence of measurements, but using a different interface to the queue server. I am again showing you the experiment on the nickel foil and the nickel oxide that I set up to measure. Now I'm showing you Ariadne, our fancy new GUI that we're starting to work on at the Beamline. I click the batch upload button. I click a few more things, and I'm going to import that spreadsheet into the Qt app. Well, I'm having the Qt app send those plans off to the queue server. There you see the contents of the queue. I can click on the individual contents, and you see the widgets for editing those things. In the case of the xas plan, it's a custom widget that was written for use at BMM in our Qt interface. There is the queue in the Run Experiment tab. I can click the Start button, and now notice the camera. You see that the slot command ran, and it rotated the sample into position. And now here in a second, here we go. The data started to stream in live. This is, again, a live presentation of the data. Again, the default presentation of the data is to show you, in the case of transmission data, the natural log of I0 over IT. That is, show you the xas data. The other tab shows the I0 data streaming in. And that's how we chose to display the data at the Beamline. Now, there's 2 big points that I want to make as I'm showing you the same measurements over again in the Qt app. One is that the queue server component is, as Dan said, it's independent of the GUI interfaces. The web app was talking to the queue server. The Qt app was talking to the queue server. They could, in fact, both be talking to the queue server, both be examining the queue, and both being displaying the data at the same time. That's the benefit of having all of the stuff that executes the plans behind the interface. So we're using common tools to develop different presentations that might be useful in different contexts. It's, for example, sort of easy to see that one might want to sit in front of the Qt app at the beamline when you're at the beamline. But if you're on a lounge chair in a beach in Maui, you might want to just point at the web browser and check out the status of the queue through the web browser. Now, the other thing I want to say about both of these apps, and I think you see it a little bit more clearly in the Qt app, which is maybe a little bit more polished than the web app at this moment, is that we're getting something bespoke out of this. That is, what you're seeing in front of you has bits that are tailored to the needs and the wants and the demands of the beamline, its staff, its visitors. This is doing what the beamline needs. It's not that the beamline is figuring out how to use a prepackaged GUI tool to do their own work. We're having the GUI tool do the things we need done at the beamline. And this was made possible in part by the investment in custom widgets, and it was made possible in part by the investment in custom bespoke plans that already existed that work in a different context and also in this context. Here you see the second scan of data is showing up, and I think, Dan, this would be the time that I'd want you to speed up the flow of time so that we can see the data showing up. Boom, boom. See, there's the difference between nickel oxide and nickel metal, a lovely little valence shift, just like you expect. So now we've measured some stuff. What next? Well, you might have noticed that there's a tab that's labeled Data Broker. And so the last quick video I'm going to show you is showing you how you can examine data from the past. So here I've started by clicking on the most recent scan. That would be one of the nickel oxide scans. I click View Selected Runs, and the standard way of displaying the data shows up. The x-axis, the I0 spectrum, and you can look at either of them. One of the killer features of this tool is that you can edit what's displayed on the y-axis. Basically, any kind of math expression using any function from numerical Python can go into that expression. Here I'm showing you the negative of the x-axis. I'm showing you upside down x-axis because, you know, that was quick and easy to type. But it could really be anything. Now I'm clicking on the two most recent scans, the nickel metal and the nickel oxide, and showing them over plotted. And so there you go. This is a lovely, quick and dirty interface that treats historical data and the data that's coming in common ways and in ways that are bespoke and useful at the beamline. Back to you, Dan.
Thanks, Bruce. I'm going to hand it right over to other Dan, who will be sharing for this portion.
All the Dans.
Thank you. Hello,
the Dan
everyone.
sandwich is complete.
I'm going to see if I can do this here to pass it to yet another temporally shifted version of myself. So here we are on the PDF beamline. This is live. You can see a view into the beamline here and here. We are a total scattering diffraction instrument at the NSLSII. Right now, the beamline is set up in the far field configuration, so you can see the Perkin-Elmer detector is about 1 meter away from the sample back here. The sample itself are right here. They're sitting on our sample bracket holder. This is another view. It's a little easier to see the samples, but they're tucked away under here. So to get started today, we connect the GUI to the queue server itself. And now we're going to make about the simplest plan we can. We're going to start by moving to a sample in this case, let's go ahead and say we want to move to Lab 6, which happens to be currently loaded onto that bracket. And then, of course, once we move there, we're going to want to take a measurement. So we tell it, hey, I'm measuring Lab 6, and maybe I want to do a 2-second exposure. This will automatically do a dark and a light. So there we go. Move to the sample, take a shot. So let's start the cue. You'll see the sample shifter move to Lab 6. You can see the plan running here, showing that's the dark image being collected. That's the light. Everything's done. Cue's empty. If we go over to the Data Broker tab, we can see the 2D detector image down here. Little spotty, but that's okay. 2-second Lab 6. And the azimuthally integrated pattern up top here. So that's all well and good. Now let's say we want to go back and measure something else. So what's nice about this GUI is rather than making those plans again from scratch, we can select these two elements, copy them over to the queue, and maybe just edit them and say, well, this time I would like to measure, let's do Syria. Let's do Syria instead of Lab 6. So we've just edited that entry. Now we can go down here, do the same thing. But what if we're not careful? We're in a rush and we misspell Syria. What's going to happen? So if we start this plan, we can see it executes the first part just fine. Oh, but it spits back that that plan. It says, look, error, something was wrong. It doesn't crash. It just lets you sort of re-examine what you were doing. And in this case, go, yes, no, I do know the formula for Syria, which is in my dictionary of known samples right now. So I can edit this and fix it and pick right up back off where we left off, measuring the Syria, and sure enough, see the Syria pattern pop in instead of the Lab 6. There's our Lab 6, there is our Syria, and the plot has updated to show the diffraction pattern as well. So one of the nice things about this beamline is, of course, we have these very mobile detectors, so we can take either far field diffraction measurements or move it in close for a near field for a PDF study. So let's take advantage of that. Let's go back, use the plan to move detector configuration. We happen to have one here today called close. And it takes about 30 seconds for the detector to move in this configuration, so we're going to start that move. But while we're doing it, we can begin to construct our next plan. So we can bring in, say we want to move to Lab 6, and we want to measure Syria again now, but this will be in the near field configuration. Unfortunately, the detector blocks the camera we were using to look at the samples, but we can see that the detector's coming in. But notice I was able to adjust that whole plan while the detector was moving, and now it's just going through and digesting everything that I put in there. And sure enough, if I look in the data broker here, as it's performing these measurements, we're getting updated images for the diffraction patterns, and we can see the near field images for the Syria and the Lab 6. And these are all being stored within our data broker here. So we can pull them up and compare them if we want to. So here we are back in the Run Engine tab, and I've already set up kind of a complicated plan for us here. We're going to start by moving the detector back to the far field condition because, well, I miss looking at our samples. And then we're going to be measuring a bunch of the samples with these sort of rests in between, this plan called Take a Nap. It's really just a rest to let the detector catch its breath, you know. But we don't want to waste any beam time while we're doing this. So I'm just going to turn on looping. And what looping does is, as commands are executed, they're going to pop to the end of the queue automatically. They're going to be appended to the bottom of the queue. This way, we'll just keep collecting data until we decide to stop. So we say, okay, so the detector's moving back. We're starting to look at our plan, and we see everything's fine, except, uh-oh, look at this. I see a mistake. Right here, instead of a single 5-second rest after the data collection, I see 3. I don't know how that happened. Now, normally you might think we have to stop the plan and start all over it, but remember, this queue remains mutable. We can safely modify it up to the point that components are being executed. So I could just go in and delete these 2 little excess take a nap commands, and we're right back to where we wanted to be. And you can see that the commands that had already been executed, moving the detector and measuring samples, they've popped to the bottom of the queue. And maybe I don't worry about moving the detector anymore, so I'll just get rid of that. And now we have this nice plan. We've sort of modified it in real time, and data's been collecting and streaming in. And sure enough, we've been collecting all these beautiful diffraction patterns. So that's pretty great. Well, we like mutable queues. So you've already seen this Bluesky queue server in action today with the web-based GUI earlier with Bruce and the Qt GUI. But I want to stress you aren't required to use the front ends we've demonstrated here today to take advantage of Bluesky Q. There's a Python API if that's your thing. You can communicate directly with the queue from a terminal. Essentially, we don't want to limit how you or your beamline or your users could possibly take advantage of this capability. So just to show off, if we go back to the run engine, we can see we're still collecting data, right? There's some empty cap done. While we're running, let's go ahead and add some more plans to this looping list via something else. How about a terminal? I bet if you personally hate GUIs and you've been gritting your teeth this whole time, I bet you like working in terminals. Well, we got you covered. Let's go ahead and say, the beamline's been working hard. Let's add this silly little plan, take a nap for 60 seconds. Let's put in a minute-long nap. Say, PDF, you know what? You've earned it. In fact, let's put in 2. And if we go back and look in the application and looking at the queue and scroll to the bottom, what do you see? We've added in those couple of take a 60-second naps by communicating via the terminal. Now, obviously, this is kind of a silly example. You wouldn't really do this, but it demonstrates the functionality is there. I see a lot of promise in this capability, particularly for things like adaptive scans or for artificial intelligence and machine learning applications on the beamline. In fact, we think that this platform has real promise to be able to facilitate easier human-AI collaboration, really letting the researchers and the computers interface with the beamline on the same interactive platform, which is the Bluesky Q. So with that sort of grand promise of the future, I'm happy to thank you very much for your time and pass you back to the non-recorded Dan. So here we are on the...
Thanks, Dan. I've just got...
Turns out it loops.
You left the root button of the queue on, I guess.
That's what it was. I forgot to turn it off. You're right.
I've just got 1 or 2 more slides to wrap us up, and then we can move on to questions and discussion. Somebody holler to confirm you see slides.
Yes.
Okay, let me just advance to where we left off. Ooh, the laptop crawls to a halt. There we go. Great. So as usual with Bluesky things, we work aggressively, openly. Everything is on GitHub from the start. And this toolkit is already making a science impact at our peer facilities. I just want to mention a couple of those. NSLSII, some of our counterparts there found themselves confronted with some very urgent short-term GUI requirements from a group of users and elected to try cobbling together a GUI to meet their requirements out of this same toolkit. So it ended up looking fairly similar to the BMM and PDF Qt apps that you saw. But if you're looking closely in those demos, you'll see that what Bruce was using and what Dan was using looked a little different. So you can already see the divergence and customization. And they tried some of that, and from what I hear, it went well. For a couple months, APS 4ID Polar has been experimenting with the Bluesky widgets for visualization in Jupyter for custom live streaming visualizations for Zanes and XMCD. That's been a valuable source of feedback to the developers of those tools. And finally, you've already seen at a previous meeting, perhaps ALS showed off a proof of concept StickSim application that incorporated some of these same components for run engine control and data visualization during the scan. So with that, a couple pictures and links to the videos, which we will share sometime after this talk.